Hi, this is the next segment of case study number 2 for the Space Challenger shuttle disaster. This is a recording of the events at the Telecon meeting by Roger M. Bosley, and I will go ahead and read the events according to him. The evening Telecon meeting between MTI, MSFC, and KSC on January 27, 1986, was the final event preceding the Challenger disaster. The major activity that day focused on the predicted 18 degree Fahrenheit minus 8 degrees Celsius overnight low and meetings with engineering management and to persuade them not to launch below 53 degrees Fahrenheit, 12 degrees Celsius. My whole being was driven to action for this cause because of my memory of January 1985 participation in the inspection of the hardware from the previous coldest launch, which had massive hot gas blow-by. The discussion activity concluded with the hurried preparation of 14 view graphs by various engineering groups, which had then less than an hour to respond for the scheduled evening telecon. The following discussion is summarized to show the content of the engineering presentation. Figures labeled as view graphs show the major thrust of the telecon and contain the actual content of the originals as presented, with SI units added, while others are summarized to give general content for brevity. The first view graph was a title page. The second view graph showed a table of post-history of O-ring damage on SRM field joints. The third, fourth, and fifth view graphs are shown as figures 4, 5, and 6, respectively. Figure 4 was taken directly from the August 19, 1985 presentation to NASA headquarters. The last two statements show the reasons for both the high concern and for having a high probability of a secondary seal during the first portion of the transient time zone. The last statement was produced from testing at 50 degrees Fahrenheit, 10 degrees Celsius, which showed that a seal could maintain contact with its mating surfaces when compressed 0.040 inches, 1.02 millimeters, and only 0.010 inch, 0.25 millimeter of compression was removed from the seal. Figure 5 was the heart of the discussion at the Telecon. The engineering issue was, would the seals even actuate and seal due to changing their timing function? This would place us in the category of having a high probability of no secondary seal capability, while the primary seal would be experiencing massive blow-by erosion due to its inability to respond to the gap opening of the metal parts. The last two statements summarize the fear and loss of redundancy based upon my remembrance of the January 1985 post-launch hardware inspection. Figure 6 shows the field joint in the as-assembled configuration, plus the pressurized configuration, which shows the gap opening parameter due to outboard radial deflection of the case membrane. The differential deflection between the membrane and the stiffer joint causes the inboard clevis leg to deflect inboard opposite the rotation of the tongue, which causes the gap at the seals to open. This results in the secondary seal lifting off its seat at full pressurization without considering seal resiliency parameters. The sixth view graph shows a comparison of hot gas blow-by by comparing arc lengths of blackened grease and some descriptive phrases for various flights at different launch temperatures. The seventh view graph was a table of O-ring shore hardness versus temperature. The eighth view graph contains the preliminary O-ring resiliency data in a tabular form. Up to this point in the Telecon, I was asked several times by NASA to quantify my concerns, but I said that I could not since the only data I had was already presented and that I had been trying to get more data since last October 1985. At this comment, the general manager of MTI gave me a scolding look as if to say, "Why did you tell them that?" The presentation continued with view graph 9, which showed subscale test results of cold gas blow-by test at 75 degrees Fahrenheit, 24 degrees Celsius, and 30 degrees Fahrenheit, -1 degree Celsius, which showed no leakage. This data was used as an argument by management to say that the joint sealed at 30 degrees Fahrenheit, -1 degree Celsius. But in fact, the tests were not seal tests at all, since the test ring was a solid block of metal which did not have the deflection characteristics of the full-scale joint, and was never intended to test anything but incipient blow-by before any joint deflection occurred. View graph 10 contained a table of compression set data to aid in the visualization of seal permanent set characteristics. View graph 11 is shown as figure 7. It provided a comparison of O-ring squeeze for the Challenger joints, SRM 25, versus the previous coldest flight at 53 degrees Fahrenheit, 12 degrees Celsius, SRM 15. View graph 12 is shown as figure 8. The DM designates development motors, QM is qualification motors, and SRM is flight motors. This chart showed the current database versus the predicted Challenger seal temperatures of 27 to 29 degrees Fahrenheit, -3 to -2 degrees Celsius. View graph 13 is shown as figure 9. The third and fourth statements under the first bullet are actually disclaimers for the development and qualification test data because the joint putty had been altered after assembly and prior to horizontal test firings. Observed holes in the joint putty were repaired since it was thought that the horizontal assembly was very severe on the joints and is what caused the holes in the putty, and that vertical assembly would not cause such holes to occur. The reasoning was generally okay, but that reasoning was never tested until sometime in 1985 when it was found that vertical assembly could indeed cause holes in the putty. The major faulty thinking lies in the fact that no specific vertical assembly testing was performed to verify the original assumption, and that made the original horizontal test firings a series of successful tests without any seal erosion. View graph 14 is shown as figure 10. This concluded the engineering presentation. Then Joe Kilminster of MTI was asked by Larry Malloy of NASA for his launch decision. Joe responded that he did not recommend launching based on the engineering position just presented. Then Larry Malloy asked George Hardy of NASA for his launch decision. George responded that he was appalled at Teleconn's recommendation, but said he would not launch over the contractor's objection. Then Larry Malloy spent some time giving his views and interpretation of the data that was presented, with his conclusion that the data presented was inconclusive. Now I must make a very important point. NASA's very nature since early spaceflight was to force contractors and themselves to prove that it was safe to fly. The statement by Larry Malloy about our data being inconclusive should have been enough all by itself to stop the launch, according to NASA's own rules. But we all know that this was not the case. Just as Larry Malloy gave his conclusion, Joe Kilminster asked for a 5-minute offline caucus to reevaluate the data, and as soon as the mute button was pushed, our general manager, Jerry Mason, said in a soft voice, "We have to make a management decision." I became furious when I heard this because I sensed that an attempt would be made by executive level management to reverse the no-launch decision. Some discussion had started between only the managers when Arnie Thompson moved from his position down the table to a position in front of the managers and once again tried to explain our position by sketching the joint and discussing the problem with the seals at low temperature. Arnie stopped when he saw the unfriendly look in Mason's eyes, and also realized that no one was listening to him. I then grabbed the photographic evidence showing the hot gas blow-by comparisons from previous flights and placed it on the table in the view of the managers, and, somewhat angered, admonished them to look at the photos and not ignore what they were telling us, namely that low temperature indeed caused significantly more hot gas blow-by